This paper is entitled The Concept Solution Architecture for Electrical Distribution Control Centres. I'm Calum, Mackinnon, and together with my colleagues Matthew Hamilton, Kyle, Jennett, Euan, Morris and Rory, Telford, we were supported by two industrial partners in conducting this work: Scottish and Southern Electricity Networks and UK Power Networks. I'm based at the University of Strathclyde's PNDC, where I work as a research and development engineer. Over the next 10 minutes, I'll offer some brief background to this project, discuss our engagement with industry, and then cover 4 design iterations of the concept design that we outline in the paper. I'll briefly mention some points of discussion and collate conclusions from this 12-month project. As we look to decarbonise the energy system, demand is growing as more electric vehicles, heat pumps and other technologies connect. Increasing amounts of connected distributed generation can lead to less predictable network behaviour, including bidirectional power flows, and as a consequence of the intermittent nature of renewable resources. There's an ageing asset base, at least in the UK, and networks are seeing increasing use of digitisation and information and communications technologies. Collectively, these lead to increased alarm volumes, potentially creating a much more stressful environment and potentially inundating control engineers with more information than ever before. Advanced Distribution Monitoring Systems, or ADMS, are typically individual and configured per licence area. Vendor lock-in can arise where operators are tied to using systems from a particular supplier, and together these situations can lead to expensive and sometimes piecemeal upgrade projects for systems which are fairly distinct, and there can be a lack of coherence also from the point of view of control centre engineers. To begin this work, we facilitated industrial engagement to collect views held by contributors from a range of business areas within SSEN and UKPN as industry partners. This was informed by background reading of partner documentation. We asked what were the most pressing things partners would like to see in future control centres, along with potential opportunities or risks. We hosted 6 separate engagement exercises comprising a set of large workshops, collectively with 10 distinct breakout rooms, and a couple of unstructured interviews with small to medium-sized organisations as well. In each session we collected notes and subsequently codified each line. We then tried to combine similar or related points made on separate occasions, and gradually 13 themes began to emerge from the discussions. Design has followed an incremental approach, as you can see on the left of the slide, beginning with functions and then use cases and so on. And we find that this aligns broadly with the first 3 layers of the smart grid architecture methodology, or the SGAM, as you can see here. In the next few slides I'll cover these iterations. We took a certain approach to the design. It was to begin from a blank canvas, and the process had to account for the fact that new technologies and approaches might emerge in future, and so there had to be a degree of flexibility or option value incorporated within the design. The process also would be iterative, and it was to form an overall architecture rather than any specific details, and we would accommodate best practice wherever we could. We went through 4 iterations, first preparing the initial concept design that you can see on the right, then exploring functional requirements, and then in turn non-functional requirements, before trying to align with established frameworks. This UML use case diagram illustrates the functional requirements. Each of these use cases illustrates a kind of storyline where a certain functionality is offered within each of the components. This relates to the first half of the diagram on the previous slide, and this relates to the lower half of that diagram. In turn, then, we explored non-functional requirements by building upon those use cases and trying to specify which exact technologies might be envisaged as part of the components. And we developed then component diagrams for each of the components of the overall architecture, and in particular this provoked us to think about the interfaces which result from that. What are the data that are required for a particular component to function, and what would its outputs be? Together then we collated these individual component diagrams, and we emerged with a picture on the right where the data interfaces are shown between these components. At this point, it's important to take stock that this is a very early, a very straightforward and very preliminary investigation consisting of only 12 individual component blocks. But even at this simple, abstract level of detail, there are still 27 individual data interfaces between these components and over 40 in total. We can see that the scale of complexity desired by our network operator partners could very quickly lead to a very, very complex information system required to underpin these aspirations. In the fourth iteration, we began to assess this overall design and to begin to align it with frameworks established within the literature. This meant we first had to investigate the interfaces and decide whether or not this could be refactored to fit the framework. And by aligning with this tried and tested framework, we were able to bring in these best practices, and accordingly this promotes separation of concerns and is a step towards ensuring that the system is adaptable and maintainable in the long run. This leads us to refactor the design to that which you can see on the right, and the framework is also accompanied by a set of design principles. To discuss and draw some conclusions then, the first is to say that when we compared our own independently prepared design with those prepared by operators, there were some functionalities uniquely envisaged by each attempt, and so multiple independent designs led to a more comprehensive result when they were collectively compared. The scale of ambitions, as I mentioned in the previous slide, the scale of ambitions that are proposed could quickly lead to a very complex system, which we propose that it's possible to get ahead of by using interoperability, and which we've already seen by adopting design principles associated with frameworks and other forms of best practice design. We believe open source development offers an opportunity for a more collaborative approach to design and development of this system, and we're also aware of the fact that these systems are best tested through implementation. So as part of our further work, which is ongoing at the University of Strathclyde's PNDC, we are taking some of this work forward. And so if you have an inclination to become involved, or if you wish to collaborate with us on this or on other topics, then we'd be more than happy to hear from you. There's more information in the associated paper, and even more available through the Energy Network Association project portal, which you can ask either us or our partners about if that's of interest. And at this point, I'd like to share the references that I've used. I'd like to thank you for your interest in this paper, and I hope you enjoy the rest of the conference.